Okay, welcome to error correction session 6. Our first speaker will be Berent. The speaker will tell us about localized statistics decoding, a parallel decoding algorithm for quantum multi-PT codes.
Yeah, thanks for the introduction. And first I want to kind of say thanks to my collaborators, Timo, Armanda, Robert, Jens, and Joschka, who's also here, some in the audience. I'll be talking about a new decoding algorithm that we've developed. So maybe let's kind of set the stage. I want to highlight kind of the state of the art. So on the one hand, we have surface codes, and they are, from a decoding perspective, also very nice because they have a nice structure, which allows for what we call is matchable decoding, so matching decoding. And what this means is that essentially syndromes come in pairs for these codes. So for example, as in this figure, you can see that an error string in the bulk of the surface code implies that there's two syndromes that are kind of highlighted. And this is very nice. And again, this kind of gives us both accurate and efficient decoding algorithms for surface codes. And on the other hand, if you want to do something maybe more general, which are high-rate LDPC codes on which we have a lot of recent work. Well, in general, they're of course not matchable. And the structure is not really as nice as for the surface code. They have many long-range connections, etc. So what we do currently, especially for the finite size case, is BPOSD decoding, and I will kind of highlight that a little later what that is. And in general, the thing is with BPOSD decoding and similar decoders for general LDPC codes is that they're accurate, so they give good decoding performance, but they're kind of inefficient. So we really need more efficient decoding algorithms for LDPC codes, like to match kind of what we have for the surface code. That would be the goal. So let me briefly kind of step back and talk about the problem that we are solving with decoders, which is the syndrome decoding problem that you're all familiar with. So essentially, we have some encoded logical state and some ancillary system, and we just measure the stabilizers repeatedly to obtain a syndrome string, a binary vector. And that is exactly the input to the decoding algorithm. And the decoder is a classical algorithm that uses the syndrome string to infer a recovery operation. And for the purposes of this talk, I want to think about this circuit as a form of some linear constraints. So essentially, you can take this syndrome extraction circuit of the code and construct this check matrix H that relates circuit locations, so in the syndrome extraction circuit, to checks of the code. So essentially, you would have you construct this matrix such that a row is a check of the code, so a parity of measurements, and the columns correspond to faults that trigger these checks. And essentially, then this boils down to something that is very similar to a classical decoding problem. And the goal for minimum weight decoding, which is what I'm going to be focusing on in this talk, is that we want to find a minimum weight estimate, such that essentially the bits that we choose are those that have the highest probability of being in error. That is kind of what we want to do. And for the rest of this talk, I will kind of go back and forth between this representation of the decoding problem on a graph and on this matrix. And you can simply think about this check matrix that we construct as the adjacency matrix of the graph. Okay. So circling back to BPOSD, the BP stands for belief propagation, which is very common in classical coding theory. And essentially what you do is that you do this bitwise naive kind of search over corrections. So basically, for each bit, you compute the probability of it being an error, and then you return the minimum weight correction corresponding to that. And of course, in general, this is kind of not very efficient because you have lots of repeated summations. So what you do in the context of quantum decoding is that you want to exploit the structure of the probability distribution, which is then essentially given by the decoding graph, to kind of avoid these repeated sums. And in fact, we know that we can do this for LDPC codes very efficiently. And essentially how this works is that if we assume some error model, some probability distribution, some error distribution, then we can kind of initialize the nodes in this decoding graph and then run an iterative procedure to compute the bitwise probabilities of each bit being in error. Yeah, and you can do this with different update rules. So how this simply goes is that each node looks at the messages that it receives from its neighbors. It does some small computation, and it sends messages out to each of its neighbors. And then at some point, you would hopefully convert to a solution. And what is well known from classical coding theory is that for trees, this algorithm actually gives an exact solution, but for graphs with cycles, it's just an approximation. And to kind of deal with this is that we give an additional parameter, which is a maximum number of iterations that you would use for this repeated sum computation, so that we kind of obtain a solution. So to highlight kind of the advantages and disadvantages of this algorithm. So on the one hand side, it's very efficient. You can also parallelize the algorithm for like checks and bit nodes, and you can compute this probabilities very efficiently at least for classical codes. And as I said before, for tree-like graphs, this is like an exact algorithm. However, there are of course some downfalls, and these come into play particularly for quantum codes. So on the one hand, it is known that cycles in the decoding graph kind of deteriorate the performance of BP. And in particular, what is important for quantum codes is that if there exists more than one minimum weight solution where the bits have equal probability, then BP will converge to the sum of these solutions, and this will not constitute a valid correction. And to kind of highlight what I mean with this is that if you consider here the simple surface code and an error pattern on the surface code, where here qubits 2 and 10 would be in error. And if you run BP on this graph, then what would happen is that it would assign equal probabilities to all these 4 bits in this kind of loop, so 2, 10, 5, and 11. And the correction that BP would return would then be the sum of these corrections and the sum of these two, and this would not be a valid correction for the code. So this kind of very simple example highlights what happens if you just apply plain BP for quantum codes. So we need some way to deal with these failures, and that's exactly what OSD post-processing is doing. So to kind of tell you on a high level what OSD is doing, we can consider some check matrix of a code. And again, I want to kind of think about the decoding problem as this kind of solving this linear system. So what you might want to do is to just solve the system by Gaussian elimination, for instance. However, the problem is that you might not always be able to do that because it's not guaranteed that this matrix has full column rank. So you might not be able to kind of get the full synonym space in some sense. And the solution, and this is kind of the high-level idea of OSD, is to simply pick columns of the parity-check matrix to get like a full rank subset, and then just use this subset to solve this system of equations and get a correction. And what you can then do is you simply use the bits that you need for your correction and set the rest to 0, or maybe the output of BP. And a complication of this is that, of course, the set is, it just needs to be a basis in essence, so it's not unique. So what OSD is doing is that it takes the probabilities it gets from BP to sort the columns, and then it just picks the ones that have the highest probability of being in error until it has a full rank subset. But if we consider decoding of finite length codes, then you will see that this is kind of a not very efficient task, because even for moderately sized codes, like this 144 bivariant bicycle code, for instance, the decoding graph, or like the check matrix of the code, has over 8,000 columns. So computing this kind of Gaussian elimination is not very efficient. That's not what we want compared to linear time decoders we have for classical or for matchable codes. So what we do is kind of, this is exactly the issue that we want to tackle with our algorithm. So let me give you a brief overview of the main ideas. So on the one hand, what we observe is that errors on QLDBC codes and their decoding graphs in general have some clustering structure, and this is also what is kind of underlying some threshold proofs for QLDBC codes. So we want to kind of use this error clustering to formulate a parallel algorithm that uses this clustering on the codes. And the idea is that if we can approximate these error clusters well enough, then we have disjoint decoding problems, and we can solve all of them concurrently and efficiently. And how we do this is kind of in an OSD-style way. So we can use, for instance, soft information input, as for BP, to try to approximate the clusters. So we kind of grow clusters on a decoding graph, guided by some soft information input, like BP. And then we just form small decoding problems that are local and disjoint, and we try to solve all of them in parallel and then return the union of their solutions as the final solution. And the thing that is important when you think about doing everything in parallel is that, of course, if we try to grow these clusters on a decoding graph, and if we try to approximate the true error clusters, then what might happen is that we don't always achieve in doing that completely. So we might need to kind of merge clusters together. And this is, of course, a step that would kind of destroy the parallelism that we have. So what we really need is an efficient way to solve these decoding problems in parallel and also kind of take care of merging clusters together, essentially. And the central technique that we have for that is what we call on-the-fly elimination. And this is basically a way to compute a set of disjoint matrix factorizations in parallel, so basically just the PLU decompositions in parallel, together with a way of merging existing PLU decompositions together efficiently without additional recomputation overhead. Yeah, so this is kind of the main idea. Now let me dive into a very kind of simple example, just to give you an intuition on how this algorithm will proceed and how to kind of go back and forth between this graph and matrix picture. So in essence, again, if we consider some error pattern on the surface code, our goal is now to construct local check matrices to solve the decoding problem. And what we do is we can try to approximate the true error clusters by start to construct clusters and that are sub-matrices, so to speak, from the violated syndrome nodes. So in essence, we kind of start to construct clusters for all of the violated syndromes, and we start growing by always picking the bit that has the lowest value according to the soft information input. And by that, stepwise, we can construct these local check matrices. And in each step, of course, we need to check if we can already invert these matrices to get a solution. And at some point, it might be the case that according to the distribution on the nodes, that they want to kind of grow on the same bit, and that's exactly what induces a collision. And we need to kind of merge these decompositions or these matrices together. So that's when that's when we detect this collision. We need to merge them together in some way. So, and then we would have a check matrix such that the syndrome is in the image of the matrix. We can invert it to get a solution. Yes. Next, I want to kind of talk about this central technique that we have on the fly elimination that allows us to do this efficiently and in parallel. So in general, when solving this decoding problem for QLDBC codes boils down to solving systems of linear equations in general. So what we do is we kind of just construct the standard PLU decomposition of a matrix. And now if we think about the primitives that we have in our algorithm, that is growing clusters and merging clusters together. Well, the first thing is that if we have an existing PLU decomposition of some cluster and we want to add a column, then basically this boils down to kind of just eliminating this new column. And what is actually nice about this is that since the code is LDPC, it has constant weight, so this is kind of efficiently doable, very straightforwardly. Now the problem is that if we have two disjoint decompositions that we now need to merge together in some way, we can't do this fully in parallel anymore. And a naive method how to do this, and I think this is more or less underlying what most existing clustering algorithms do, is basically you throw away the existing decompositions, you merge the matrices together and do a recomputation of the PLU factorization. And of course, that would lead to less parallelism in your algorithm and to repeated computation throughout that we don't want to have. And to resolve this with on-the-fly elimination, what we observe is very basic that, of course, disjoint PLU decompositions kind of factorize. So they kind of have this nice block structure. And when we then go to the case of merging clusters together, we actually show that with some basic matrix operations, we can reduce this merging case to actually just adding a bit to the cluster. And this is in more detail in the paper, but just to kind of highlight how this works is simply by observing that these decompositions are kind of disjoint, and then essentially the column that induces the merge between these two factorizations can be brought into this form where we just need to re-eliminate, so to speak, the entries that are not common in either cluster. So that's very nice, and that allows us to kind of reduce this case of merging disjoint decompositions to adding a bit to the column to the cluster, which is efficiently doable. Yeah, so we've implemented this kind of heuristic algorithm. So let me briefly mention some numerical results that we did. So here we just have some basic memory experiments where we have investigated several families of LDPC codes. On the left-hand side, we have a hypergraph product family. On the right-hand side, bivariant bicycle codes, recently introduced by, or investigated by Bravi et al. For instance, for the bivariant bicycle code, it's very interesting, and that we observe, we can match the state of the art with our algorithm, essentially. So we can match the BP OSD performance while, having less overhead. Let me briefly summarize what the main ideas behind this algorithm. So the central idea is to exploit this clustering, this error clustering on LDPC codes, and to have a parallel algorithm for that is very efficient, especially in the finite-sized regime. We match the performance of the state of the art, numerically at least. We also, I didn't talk about this, but we also have some higher order reprocessing, and for BP, so let me briefly kind of say what that means. For BPOSD, you can do kind of higher order reprocessing of your solution to find a better solution, so to speak. So if you choose your columns, it might be the case that the columns that you choose are not linearly independent. So the columns with the lowest probabilities or the highest probabilities of being error might not be linearly independent. So then what you can do is you can kind of try to do a search through multiple possibilities to get a better solution. And we have implemented a kind of localized parallel version of this as well. Yeah, we hope that maybe the on-the-fly elimination may prove useful beyond QEC, in any case when you need to solve lots of linear equations and have either a parallel algorithm. Yeah, we also have an open source implementation. You can happily try it out on your favorite LDPC code. And then maybe to highlight some open problems. The algorithm I presented here is, from an analytic perspective, a heuristic, so we didn't prove any performance guarantees, unfortunately. But I believe that this would be kind of an interesting open problem, and I think that clustering techniques from QLDPC code might really help here. And maybe a related question is the potential of error floors for these decoding techniques, because at least I'm not aware of any analytical guarantees for decoding QLDPC codes with BP or BPOSD, and these are the golden standards, but I don't think we have a very thorough understanding of them analytically, and I think this would be very interesting. So yeah, with that I conclude, and yeah, thanks.
So I have a couple questions. So first of all, for OSD, the asymptotic performance is something like n cube.
Yes.
Do you have an estimate of what this performance is here? What is it?
Yeah, we have some crude analytic bounds that depend, but essentially the punchline is it depends on the size of these local clusters, and we have some. Maybe I can just flash this slide really quickly. I have some backup slides. We did some investigations, some numerics to estimate the size of the clusters in LDPC code. I think this is for the 144 bivariant bicycle code. And you can see that the average size of the clusters and the maximum size of the clusters are really small. So solving these local systems amounts to, what are values, good values here? In the low error rate regime, the maximum cluster size is something like 10. So inverting a matrix with 10 columns, essentially. That would be assuming you have enough parallel resources.
So basically you are saying without parallelism it would be n times some n cube where little n cube where little n is the size of the cluster.
Exactly. So the thing is that I guess in a high error rate regime, when you essentially cover a large portion of the graph, it's basically OSD decoding. Yeah. So you would invert the whole matrix essentially.
Right.
Yes.
And then do you have like numerical comparison of the speed with say BPOSD?
That's a good.
It could be. Yeah. It doesn't have to be precise.
Yeah. I have also a backup slide on this. Maybe something to point out is here that I think the comparing the runtimes is like a little intricate, because I mean here we compare with BPOSD in 2 different implementations, and the thing is that both LSD and BPOSD have BP as kind of this preprocessor, so it's not really how do you estimate this kind of combination of decoders, and then of course we have a prototypical implementation that is not fully in parallel. So yeah, I don't think these numbers say a lot. But just if you run it on your laptop right now, then that's basically the performance you will get. And you see that, I guess the punchline of this plot is that here we plot both the time needed to do the BP iterations and also the time to do the post-processing, LSD or OSD. And if you look at the numbers between LSD and OSD, you kind of see that for LSD we're kind of limited by the time it takes for BP. So essentially, LSD doesn't introduce too much overhead compared to BP, which is not the same for OSD, where you have quite a gap between the two. Pardon? Oh yeah, I mean these were just we just decode this code instance under some simulations, and it's not a real-time decoder. Yeah, we don't claim it, but I think it's a good path in the direction of real-time decoding.
Other questions?
Thank you for the nice talk. You mentioned the current implementation was not fully parallel, and that's what I remembered from the paper, but I didn't quite understood it at the time. Can you comment more on that?
Yeah, so we kind of have a serial implementation currently of the algorithm that does this, I would say, smart cluster merging. But yeah, I think for a fully parallel implementation, you need to be really careful about parallelization overhead and how you kind of, about the whole architecture of the algorithm. So we didn't go into too much detail. We give a parallel algorithm in our paper using an efficient parallel data structure to keep track of the clusters, but we haven't implemented this in software.
Okay, because I like the central technique being on-the-fly elimination, I think the main advantage was also that it could be done on parallel, but there is no implementation of that so far. That's my understanding then.
Yes, exactly, yeah.
Right,
so we give the parallel algorithm, but it is not in software.
Right, thank you so much.
There's other question, we'll take one.
Thanks for the really nice talk. Since there's some extra time, I thought I'd ask a non-error correction question, but I wanted to ask if the solver can be used for just solving equations fast in general. It seems like the major optimization is just a linear system solver, or is there something more specific in the problem setup here? Is this as general as just any linear system solver, or something about the decoding setting makes it more specific?
No, I think at the heart of it, it's really just solving systems of linear equations that are sparse. That's what I meant with the last, like this open problems point on the slide. That, I'm not an expert in this, but I think for recommender systems, etc., you have to kind of solve lots of linear equations repeatedly. So we were thinking that maybe in these areas you might also get a benefit of doing this in parallel and without additional recomputation overhead.